Te veo.
Ponte tú en Bueno. Voy a esto todavía. El audio debería estar.
¿Paso con el mouse?
Sí.
Ah, ¿con esto?
Sí.
Ah, a ver cómo es. Cuida.
¿Ese es el láser?
Este es el láser.
Sí. Y luego las flechas para... Este es el mío, es el tuyo, ¿no?
Este es el mío,
vale.
esto es todo mío.
Mira, gente que sabe.
Motorola.
Sergio bajo algo.
Ah, muy bien, muy bien.
Vale,
excelente.
Entonces aquí ya está, lo que no sabemos si se está viendo bien en Zoom. ¿Puedes preguntar en Zoom si se está viendo bien? En YouTube sí, porque YouTube yo sé que está retransmitiendo bien.
Okay. Dale.
Hola, ¿se oye bien en Zoom?
¿Podré poner
Sí, claro. Lo que pasa es que aquí, como está la retransmisión, no vas a...
Listo. ¿Cómo quedamos para cada tanto chusmear un poco la filmina?
Lo que veis aquí es...
Si quieres, te puedo quitar esto. A ver, puedo quitar esto para que... Yo no sé si están las herramientas del presentador aquí.
Ah, como para que vea. Ah, bueno, puede ser.
No, porque esto es Google, no tiene herramientas de presentador. Vamos, que yo sepa.
Claro, no.
Entonces, pero sí que puedo hacer para que veas esto, eso sí.
Está bien. Y eso, a ver, si paso.
Sí, puede tardar un poquito. Pero no, es que tiene, para que pases tiene que estar pinchado aquí ahora.
Ah. Excelente, listo.
Tiramos un pelín para que ella no esté muy pegada a la pizarra.
¿En qué?
Para que se la vea.
No, bueno, pero se la ve también aquí. O sea, esta es un poco la de oír ambiente. Esto es más que nada para que si quieres escribir algo.
Claro, sí.
O sea, aquí lo único que es verdad que te está pillando esa cámara. Entonces,
Esa.
Sí, para que se vea un poco la pantalla, donde apuntas. Pero si quieres que se te vea bien...
Ah, acá está, no me encontraba en la pantalla. Perfecto, bien.
Y entonces luego si quieres escribir aquí para que lo vean en detalle, si quieres escribir algo, y el sonido sale, te lo pilla por aquí, con lo cual te lo voy a poner lo más cerca posible. Y otra vez, casi te está.
Bien, perfecto.
Esperamos un minutillo y...
No.
Tenemos una cita de facultad, cita de facultad, la facultad. También tenía clase y debía haber terminado la misma. Eso. Sí, no, para ver si.
I think we can start. Oh, no.
Everyone, I hope you all had a great summer and enjoy your holidays. Today is a pleasure to introduce you Paula López. Paula is a PhD student at the Instituto de Astrofísica de La Plata, Argentina, under CONICET, supervised by Dr. Sofia Cora and Cecilia Scannapiero. Her research focuses on the formation and evolution of galactic structures such as disks and bulges, as well as the physical processes and environmental factors that influence them. Recently, she has been investigating galactic bars in a cosmological context using a TNG-50 aerodynamical simulation from the IllustrisTNG project. She also collaborates with Francesca Fracodi from the Durham University in UK on studying boxy, peanut-shaped bulges in bar galaxies seen in an eight-term projection. This project, utilizing Auriga cosmological simulation, led her to research stays at Durham University and Max Planck for Astrophysics in Munich. As part of this project, she is also involved in the GECO collaboration and IALP MUSA large program. Today, Paula will present on the topic from bars to boxy peanut bulges. So thank you very much, Paula.
Okay, thank you. So, hi everyone, I'm Paula. So, as already Enrica said, I'm based in Argentina. I'm doing my PhD there, but I'm also working with the Galaxy Dynamic group from Durham University. So, now I'm here because I am doing a research stay there in Durham, and I will be there until the end of November. So, okay, so I wanted to talk to you about bars and boxy peanut bulges, and I will be focusing on the formation mechanism and evolution using simulations, cosmological simulations. So I thought that it would be nice to have in mind some big questions that are usually addressed in this field, and we are going to talk about a little bit about this, and I will try to answer these big questions through the presentation. So I will be talking a lot about bars, so it will be good to ask ourselves how a bar can be defined, also how they interact with the galaxy that hosts them, and finally, if we go into the beginning, how a bar forms in the first place, what is known about the physical processes involved in the bar formation. So I will start with this introduction that I will try to answer these big questions. And then we are going to have a base to talk about a recent paper that I published this year, that is bars in TNG-50, where I focus information mechanism. In this work, I try to answer how the bar forms, try to characterize this structure in these simulations, and evaluate the efficiency of different stability criteria that are usually used in semi-analytical models. And finally, I will talk about the project that I am working on currently, that is boxy peanut bulges in Auriga simulations. And here I am focusing also on information and evolution process. So let's start with the introduction. So one of the big questions was how a bar can be defined. So in here we can see a very nice picture of a spiral galaxy We can see the spiral arms, and I overlay a blue rectangle in this image to see the inner region. We can see this elongated structure. We can think the bar from a morphological point of view as this elongated structure in the inner regions of the galaxy. And we know that almost 2/3 of the spiral galaxies in the local universe have a bar structures. That means these are very common features among galaxies, so that's why one of the reasons why they are a very interesting structure to study. But we can think also from a dynamical point of view, the bar as a solid structure that is rotating to a certain angular frequency, and that is made by stars. But the stars that made the bar are very particular because they are in resonance orbits, meaning that the orbits of these stars have a radial frequency, azimuthal frequency that are proportional to the angular frequency of the bar. So basically, from the dynamical point of view, the bar is made by resonance orbits. So, okay, as you can see, there is not one way of defining the bar, so we can think about these different definitions. So now we know what is a bar. Now let's think about, we have a galaxy, now we have a bar, we know what is a bar, but how is the interaction of this structure with the rest of the galaxy? So the bars are involved in the secular evolution of the galaxy. One of the things is that can influence the dynamic of stars. The bars induce different motions in the stellar orbits, and because of that they can form spiral structure, rings around the bar. And they also influence the gas within the galaxy. The bars produce shocks over the gas, and the gas is forced towards the center region. So then, when you have bars, it's commonly you have a big amount of gas in your inner region. And if you have a big amount of gas in your inner region, it can produce bursts of star formation. So the stars can act as sites of active star formation too. One of the things that I say is that when the gas is towards is forced towards the center, to the inner region, it loses angular momentum. So if you have a bar, it can produce a redistribution of angular momentum within the galaxy, mostly from the inner disk to the outer disk and to the head. And finally, due to vertical instabilities, some barred galaxies can experience this instability, vertical instability with respect to the disk. And because, as a consequence of that, can be formed structures in the central regions, there are the ones we call boxy peanut bulges that I will be talking later. So these are boxy peanut bulges because, as we can see, for example, this is an edge-on projection of a galaxy, and we can think that it has in the inner region a structure that seems like a peanut. Some of them are more boxy or X-shaped. And then we continue to, okay, now we know what is a bar, we know how it interacts with the rest of the galaxy, but what about the formation of the bar? What are the physical processes that are involved in the bar formation? So basically, you have a stellar disk, and you need that your stellar disk becomes stable to have a new scenario where the bar can form. And how you produce instability in your stellar disk? This could be through internal processes in redistribution of the mass in the internal part of the galaxy, or due to external processes such as interaction with other galaxies, mergers like BICE, interaction with cluster. So there are different scenarios where you can have this instability and then you can form a bar. So with all of this in mind, I will go to the recent paper that I published, that is in TNG 50. So in here we use this dynamical simulation where we wanted to do a specific study. We didn't want to do a statistical one, but to take some particular galaxies and do a very detailed analysis. So to do that, we use the TNG 50, that is one of the 3 TNG simulations from the IllustrisTNG project. And as we can see here, this plot, it has a lot of different simulations, and basically it tells you the information about the number of galaxies that they resolve, the mass resolution, and also the simulation volume. And if we see in this, in between these three simulations, TNG50 is the one that it has the smaller box, but also it has the better mass resolution. And as we wanted to do this detailed analysis, it was a good choice to use this simulation. So we start to we select a sample of galaxy. We took 8 galaxies. So it's a very detailed analysis. From the catalog from the Rosa Rivera 2022, in that paper, the author studied a lot of properties of galaxies, comparing barred galaxies and barred galaxies. So from that catalog, we took 4 galaxies that had a bar average of 0, and 4 of the other do not have a bar average of 0. See, here's an example of the different projections, face-on, edge-on, and end-on of a barred galaxy. And then we were interested in study different properties, how the different properties evolve with time. So to do that, one of the things that it was important to identify is when we have a bar and when we don't have a bar. Because these galaxies have a bar average 0, 4 of them, but an interesting question is to know in which time that bar forms. Because if we know the time formation of the bar, we can know the physical processes that happen before and after formation of bar. And to do that, we study the parameter called strength, the bar H2. That is a Fourier decomposition. You have your stellar distribution, the stellar density in your face-on projection, and this parameter measures the degree of axisymmetry you have in your distribution. So then you have your radial distribution of stars, and you can calculate this Fourier mode. And if you have a signal, you will have a bar at certain points. And if you don't have a bar, you won't have a signal. So we use this, we calculate this for every galaxy and another time. And we took the maximum of this curve and construct a plot like this. Here we can see how is the evolution in time of this H2 parameter, the maximum. So we define a threshold and we say, okay, when this parameter is larger than that threshold and continue growing with time, then we can define that time as the formation time of the bar. So here we have our 4 bars with the time formations, and one of the things that we notice is that the time formation are diverse. We have only 4 galaxies, but we have also very diverse time formation. 2 of them form very early in the simulation, and the other 2 have a more recent formation, but either way, they have a lot of time to evolve after the formation of their bar. So one of the things that I say is that we can think in the bar as this solid structure that is rotating to single certain angular frequency, and it's a very interesting properties of this structure. So we calculate the evolution of this angular frequency that is called pattern speed. So here we have our 4 barred galaxies, and we took the evolution from the time formation of our bar, and the thing that we found is that this pattern speed seems to increase after bar formation, and at a certain point then start to decrease, and until it reaches 0, right? And this decrease is consistent with the transport of angular momentum. The thing that I say, okay, you have a bar, it happens by distribution of mass and transport of angular momentum for the inner region to the outer region. And one of the things that we found also was that this decrease in the pattern speed of the bar was accompanied by the increase in the bar length. So with time, our bars are growing and the pattern speed is decreasing. So, okay, it's consistent with the transport of angular momentum. I say from the outer to outer disk and to the halo. So, okay, one thing to see is the halo spin. The halo spin is this dimensionless representation of the angular momentum of the dark matter halo. And it was interesting to see what was happening in here. So, as you can see, this parameter Depends on the angular momentum of the halo and certain properties, radial mass, radial radius, and the circular velocity of the galaxy. So here we have, as an example, one of the barrel galaxies. We have in the upper panel this parameter, this halo spin, evaluated in a central region of 10 kiloparsec mole. And then in the lower panel, we have the halo spin for the whole galaxy. The vertical line is indicating the time formation of that galaxy, of that bar. So we did this with the whole sample. This plot is the same that I showed before, but we have in the left side, the barred galaxies, and in the right side, the unbarred one. And we found that in this internal region, or a concentrated region of 10 kiloparsec mole, the barred galaxies have an increase, most of them have an increase with time of the halo spin. Meanwhile, the unbarred one seems to have a steady evolution. But when we see the halo spin in the total in the whole region of the galaxy, we can see that they seem to have a behavior that is quite similar. And another interesting thing that we found is that they have similar initial values for the halo spin, but regarding that, the evolution is quite different. So in here we see difference in the halo spin in an inner region, we can say, with respect to the total. So say, okay, let's go to see what is happening here. Here we evaluate the mass concentration in the inner region. So here we have the plot, again, as an example, one of the barred galaxy. We have the circular velocity approaching 0 for the total contribution and the different contribution of the star, gas, and dark matter. So we calculate this for the whole sample. We have the 4 barred galaxies in the upper panel and the 4 unbarred ones in the lower. And one of the things that we found is that in the barred galaxies, it seems to have a peak, so a peak in the inner region, and the contribution to that peak is becoming from the stellar component, thing that doesn't seem to happen in the unbarred galaxies. But until here we can say, okay, but one of the things that happen if we have a bar is these shocks over the gas, concentration of gas in the inner region that can produce bursts of star formation. So maybe it makes sense that you have this big concentration of a stellar contribution in your inner region. So to evaluate that, we say, okay, let's go to the time formation of the bar. The upper panel is the 4 barred galaxies evaluated at the time formation of the bar. And even in this exact moment when we identify that a bar form, we have the peak. And in here, it didn't pass enough time to this process act. And then we say, okay, to be sure, we can go 1 gigayear before that. And even that, in some of the galaxies, we can see a peak whose contribution comes from the inner region. So it seems to be important, the contribution of the stellar components in the inner region. Another interesting thing of this is that in the barred galaxies at redshift 0, we can see that in the internal region, the gas is almost dropped to 0, consistent with this behavior that I was talking about, the consumption of gas in the inner region into stars. Okay, to say, okay, let's do a more detailed analysis about this. So let's see how is the contribution of stars and gas in the inner region relative to the dark matter. So here we have the fraction of the stellar mass relative to the dark matter in an inner region that we define of 1 kiloparsec mole. And we can see here that the evolution is quite constant, but steady with time for both samples of galaxies. But in general, we can see that the barred galaxies exhibit a more concentration of a stellar component relative to the dark matter in this inner region. And then we have the evolution of the gas. Here again, we have the fraction of the gas relative to the dark matter in this given region. And we can see that in general, it seems to have more larger gas reservoir, the barred galaxies, than the unbarred ones. And here we can see this drop of the gas in the internal regions. This was a very interesting thing because when you do the plots, the phase-on plots of the gas component, you can see a hole in the inner region that is a feature that we didn't found in the unbarred galaxies. That we see that the gas is going smaller with time, but it is not zero as in the barred galaxy. So in general, we can see that even prior bar formation, the barred galaxy seems to have a more baryonic concentration in the inner region. So that's about the characterization of the properties of the sample. Now we wanted to go a little bit further and see how different was the efficiency of different instability criteria that are usually used in, as I said, in semi-analytical models. So as I say, basically to have a bar, you will need your stellar disk become unstable. A favorite scenario for a formation bar occurs when instability is triggered in the stellar disk. And to study this instability in semi-analytical models, they use different parameters. One of them is the global gravitational importance of the disk. Here we have this fraction where we have the circular velocity of the whole galaxies evaluated in a stellar half-mass radio, and then you will have the maximum of the circular velocity of the dark matter component. So if we have that this parameter, we are going to have it in here in the y-axis, and we have if this parameter is bigger than 1, this means that the disk is becoming more important relative to the gravitational component, the dark matter component, meaning that you will have an instability in your stellar disk. And another parameter measures the relative importance of the disk and the dark halo. Here we have again a fraction of the circular velocity evaluated in this radio against this is the circular velocity you will have only stellar component. It's the definition of the circular velocity, but it's evaluated only using the stellar component. And again, here we have this parameter in the x-axis, and we have that this parameter is lower than 1, or in some semi-analytical codes, they use 1.1. That means that if this is less than 1.1, you will have a big contribution of the disk against the whole galaxy, and you will have an instability in your disk. So, combining these two, by the combination of these two parameters, we can define an instability region. So, the thing that we evaluate was how our bars and unbarred galaxies was in this plot. So, the triangles are the barred galaxies, and the circles are the unbarred galaxies. And this is a plot that is evaluated at a certain point of time. The barred galaxies are evaluated in the time formation of the bar. When the bar formed, the disk was unstable, it wasn't. And then for the barred galaxy, we don't have a time for bar formation associated with this galaxy, so we took an arbitrary time of redshift 0. So these are evaluated at redshift 0 in this plot. So good. It seems that the combination of the two parameters is good to tell us if we have our stellar disk, if we have instability and inner in our stellar disk. Sorry. Okay, so this is good, but as I say, this is evaluated at a point of time, so it will be good to see how these parameters evolve with time. And to do that, we have in here the f-disk, one of the parameters, and for our barred galaxies and for unbarred galaxy, how this f-disk parameter evolved with time. And we can see that, okay, for the barred galaxies, that this parameter is telling us that this is unstable and almost for the entire evolution of the galaxies. Meanwhile, in the barred galaxies, it never become unstable. So it seems to work very good. And the other parameter is more messy. We have in the barred galaxies that we have an instability in our disk, even prior bar formation, but also after. So this is giving us an idea about how is the stability of the disk, but it's not a thing that we can use as a predictor of bar formation or not, clearly. So we have in here unbarred galaxies that, again, as I told you in the plot that I showed before, I evaluate this combination of parameters for the unbarred galaxies at redshift 0. And we can see that, okay, at redshift 0, it seems to be stable, the disk. But before that, it's unstable. So in semiotical models, they use this parameter. That seems to work very good. But it's interesting to see that it's tricky to have one parameter that can predict if you will have this instability or not. In hydrodynamical simulation, there are also a paper from Algori 2017 where they evaluate also a combination of different parameters to see the stability of the disk, but they use it in the Eagle simulations. So I think that it's not, there is a lot of things to see in here, and also it is interesting to study if there are other parameters or other combinations of parameters or properties of the galaxy that can tell us more about this. So the takeaway of this first work was that, okay, we can see that for both galaxies with bars and without bars have similar initial spin values, but they evolve very different, and the evolution seems to be very different if you see the inner region or the outer region. And they also have a more amount of gas star in the central regions, and it seems to be a growth of this quantity with time. And because of that, it seems to have a very significant role of the dark matter distribution to stabilize the system against bar formation. So now I will be talking about this new project that hopefully will be in archive in the middle of October. That is about boxy peanut bulges, also using hydrodynamical simulation, but this time in Auriga simulation. So, as I say in the first slide, some barred galaxies can experience some vertical instability, and as a consequence of that, we will have these boxy peanut bulges in the central region. It has this kind of morphology. And it has been observed a lot of galaxies. Here is a very nice one. We can see this pattern of an X shape. Here's another. This is very clear also. Here is more peanuts, and here's another one. And these boxy peanut bulges are, in fact, they are part of the bar. It's like in the literature there are a lot of this, but if you have a bar face on and you put it edge on, you will see a boxy peanut bulge if in that bar having this condition of vertical instability. If you have a barred galaxy with this structure and you see it edge on, you will see this. So if you see a boxy peanut structure, that means that that galaxy has a bar. But because it's not easy to have a very accurate frequency of this structure, because if you see an edge-on galaxy that it doesn't have a boxy peanut bulge, could have a bar or not. But the important thing in here to have in mind is that the boxy peanut bulges are bars seen edge-on. It's another projection of the bar. So in this case, we use the Auriga simulation that basically consists in 30 halos that reproduce properties similar to the Milky Way. And our goal is to analyze the formation and evolution of the boxy peanut bulges and compare them with the observations. So to do that, we analyzed the whole sample of galaxies of the Auriga simulation, and we found that of the 30 halos, 20 of them are barred galaxies, and from the 20 barred galaxies, 9 of them have a boxy peanut component at redshift 0. Here's an example of one of the boxy peanuts that we studied. The Auriga 13 is one of the galaxies, and we can see here the face-on projection of the stellar distribution, and here the uncharted mask, and we can see how clear is the feature. And in the vertical lines is shown the size of these structures that we found that in almost all the galaxies it represents the 60% of the size of the bar. So you have a bar and you have 0.6 of the size of your bar, you will have your boxy peanut. So they are smaller than the bar. So again, we want to do an evolution study. So we need to identify at every time if we have a boxy peanut or if we do not have, when this boxy peanut formed. And to study that, we thought about trying to do something similar as we did in the bars, that we have the H2, this Fourier mode of the density distribution or your stellar component, and that measure a signal if you have a bar or not. So try to find a parameter that allow us to measure that, the presence of the boxy peanut or not. And after analyze several parameters, I found that the best of them, the best work, is the median of the absolute value of the Sept coordinate. It's a long definition, but basically you have your Sept coordinates, and you took the absolute value, and you took the radial distribution, and you will have, and you took the median. And you will have this evolution. So again, here's Auriga 13 as an example, and this set is this parameter, and for example, here we have the evolution with time. The colors are look back time. So 0 means redshift 0, and then we go back in time. And we can see how at 3 gigayears before redshift 0, we don't have a boxy peanut because we don't have this peak that we would expect to have a boxy peanut. And then you can see how with time is growing, and then you have this structure. So we can do an analysis analogous to the one we did with the H2 mode in bar. And then do plots like this. Here we have Auriga 13, and we have the evolution of time on the thing that we call the boxy peanut strength. That it will be identifying the peaks in these plots. And doing this, we can see at what time the boxy peanuts emerge. And then we will define with this time formation of the boxy peanut, and it's very interesting because you can do it in a very automatic, with an automatic method, with a script. You don't have to see one by one the galaxies. But of course that we evaluated the efficiency of this method, and we found that there are some galaxies like Auriga 18 that, again, this is the boxy peanut strength. Here we have the time formation that we detect with our method, but we look for every snap in the simulation, and we see there are 2 galaxies that seems to have a weak structure at some point, 5.5, 6 gigayears in look back time. We see that this galaxy seems to have a boxy peanut structure, but it's only present for a couple of snapshots. It's not always present. So we wanted to take into account this time, because visually, if you do a visual inspection, you will see something but then disappear. So it's something to see in a more detailed way. And then when we have the time formation of the boxy peanut, it's an interesting question to ask ourselves how it's related with the time formation of the bar. Because you, as I said, the boxy peanut is part of the bar. So you will have a bar, the bar will evolve, and at some point of the time, it will form this boxy peanut. There is a time scale in between these two events. So to study that, here we have, here we have this plot when in the x-axis we have every galaxy, and in the y-axis we have the different time, taking the time of the bar and the time formation of the boxy peanut. For example, 0 means when the bar formed in each galaxy. The one line means 1 gigayear after the formation of the bar of the corresponding galaxy. And here in the stars we have the time that we detect a formation of the boxy peanut with this script, with this code. And we can see that in general, we see that the boxy peanut formed in between 1.5 and 2 gigayears after bar formation. So it seems to be a very quick process in between the bar forming, happening something that I will talk later, and then you have your boxy peanut. Yeah? And of course, we overlay the visual book that I was talking about, like this structure. That, for example, Auriga 18 forms the bar, and then we detect that almost 7 gigayears after the formation of the bar, you can see a boxy peanut. But close to 2 gigayears after the formation of the bar, it seems to be unstructured. So again, a lot of things to analyze in here. And as I said, what happened for a boxy peanut form? So then we enter with the bucklings episode. What are the bucklings? So you have your bar, it could happen these vertical instabilities, and basically your bar start to bend. It happens, this is oscillations, a bending, a break in the midplane symmetry of your bar, and then is when it starts to grow this boxy peanut. We evaluate that episode with some parameters that measure about, is also a Fourier decomposition and measures this amplitude of this buckling, of this bend, and theta tilt is the orientation of the stellar velocity ellipsoid and the Earth's plane. These are, if you want to discuss it later, but these are parameters that were used in n-body simulation. So again, this was interesting to see how they work in a cosmological context. And we can see here that if we have a peak, that it tells us that these parameters are measuring this bending, and the gray areas are the times when we detect a buckling by looking the galaxy, by looking the H1 projection. And as we can see, for example, Auriga 17, it has 2 buckling events. So it doesn't seem to be related only to the formation of the boxy peanut, because then you have a boxy peanut, you have very nice symmetry in your own projection, but later it will happen another buckling event. And then it's also interesting to see how the buckling episode affects the bar, because again we have our bar structure. When the bar starts to break this symmetry, what happened with the strength? And we found that the strength of the bar become weaker with these buckling events. Become weaker after the first episode, start to grow again, and then start to weaken in the last snapshots. And so one of the things that we conclude from here is that the use of the parameters used in n-body simulations are challenging and not straight. They are not working in the same way that they do in the n-body simulation, so we have to be careful with this. And that the presence of these buckling events seems to weaken the bar. here's an example of this Auriga 17 and how you will look these buckling events. Here we have, in these two first plots, we have the density distribution in the ancient region and the sharp mask, and then we have the second buckling. But you will see in every plot that there is this break in the mid-plane symmetry. There are very nice plots. It's really, you can see it. And it's really interesting to see that a galaxy can experience more than one buckling event. And you can see that these two buckling events happen at different times in the evolution of the galaxy. And finally, we evaluate also how frequent are the boxy peanuts in this simulation, in the Auriga simulation. Here we have a plot the evolution of time of the bar fraction, because to have the boxy peanut fraction, we need to have the bar fraction, because it's the number of barred galaxies that host a boxy peanut. So first of all, we evaluate the boxy peanut this bar fraction, and over that we evaluate the boxy peanut fraction. And these symbols represent observations. And in general terms, it seems to be very, very near to the observation. They are in agreement. And we found that 40% of the barred galaxies at redshift 0 have a boxy peanut in this simulation. So almost half of the barred galaxies host a boxy peanut, which so also is a very common feature in this kind of galaxies. So as a takeaway from this project is that we found a temporal difference in between the formation of the bar and the formation of the boxy peanut that is in between 1.5 and 2 gigayears after the formation of the bar. Out for 6 of our 9 galaxies, because there are a couple of galaxies, 3 of them that have a formation that is later, and the formation of the bars. We found several galaxies exceeding a double buckling episode, 5 of the 9. And also, there are another galaxies that showed buckling events at redshift 0, so now there are on that episode on buckling. And almost half of the bar of the simulation present a boxy peanut structure. So, thanks.
Thank you very much, Paula.
Thank you.
For the talk. Now we have time for questions.
Yes.
¿Tengo que hablar algo para que se me oiga o se me oye?
Yo creo que sí.
This is not my field, so this may be a very basic question, but you have been talking about boxy peanut.
Yeah.
But I have only seen peanuts.
Yes.
Where are the boxes? Are they same things in for different places?
Yeah, they are called like that because more from the morphological point of view. You could have more boxy peanut, you could have more peanut, and you also along the evolution you could have like a change in the morphology. But the things that make that shape are in which resonance are the orbits of the stars. I don't know if you are asking. No. Tell me again.
No.
You are not seeing boxy.
I mean, peanut is narrower in the center, wider in the borders.
Mm-hmm.
I assume that boxy is wider in the center, narrower in the
border. It's more boxy. Yes.
Like a square.
Yes. It's a thing that most of the galaxies in this simulation at least are more peanut shaped. But in the literature, you say boxy peanut bulges, like a whole structure. But it could be more boxy or it could be more peanut.
Mm-hmm.
But in particular here we have more peanut shaped.
And what makes the structure more boxy?
I will say that you will have. You will need to have a study about the resonance. You will need another resonance in your galaxy that have more square shape form. It depends on the orbit of your stars. it depends on the orbit from the start. In fact, one of the things that we wanted to do with this project that it became so big that we separated two papers is to do a study about the orbits of the stars and to see how are the orbits that form these boxy peanuts. Because, see, yeah.
No. It's different. It's a different question, but you are seeing the structure edge on, but edge on could be like this or like this. You could have the bar in front of you.
Yes, of course.
What happens if you are looking at the bar?
Yeah, maybe you won't detect the boxy peanut.
No?
No, exactly. That's a thing with observations. You have like a lower limit in your fraction, because it could happen that you could have also a bar face on, and maybe it has a boxy peanut, but you will know. There are some observational studies where they study the form of the isotopes, and they see that they have these spurs in your face on projection in the outer part of your bar, and that could be related with the presence of the boxy peanut, but it's challenging. You need a good inclination to detect it. In observations, in simulation, it's like you rotate in the reference system that you want. Yes. So yes.
What about the?
It's a pretty obvious question, but why only for galaxies in your first study? I mean, it would be nice to have a range in masses, types, environments. Why only for galaxies in your?
Yes, of course. I know it's a very common question. Yeah. But when we start the work, we wanted to do this. Okay, we took a few galaxies and we did do a very. I mean, if you have a statistical sample, you will have to do a statistical analysis. But here is like, I have this galaxy, what happened with this galaxy? So the focus of the work was more particular. There is the project of doing with more galaxies, but we did so many work that we say, okay, let's close this and then, but yes, it's because how we started to work with this. But of course, it's really interesting to have
that
to more galaxies. Yes, that's right. Mm-hmm.
And now that we are talking about the 4 galaxies, one of the galaxies is where B3 is completely different. What is happening with that?
Yes, it is. I think that is one. I think if I can look for it, but I think that is one of the galaxies. There is in a very dense environment. So another interesting word to see is how the environments influence in the I don't know in the formation of the bar, but in their evolution, because there are works also that they did studies about galaxies in environments, and they didn't found a correlation between environment and formation of the bar, but clearly it's influenced the evolution. So yeah.
Yeah, my question was related to that. So, what happens if you consider this satellite galaxy, for example, crossing the disk because they produce instabilities in the
Yes. I mean, because one of the mechanisms that can produce this instability is the merger. But again, it could be related to the thing that I took a small sample of galaxies. But the mergers in these galaxies didn't have impact in the formation. It was pure secular. I couldn't find any merger that is related to the formation of the bar. I didn't put it because it was very long. But yes, I did analysis on this particular. But it could be, yeah. But in that way, it's interesting to do a bigger sample to approach that. Yes.
Well, I have a question about the interesting plot when you show the delay, you can say, in the formation of the bar and also the boxy peanuts.
Here, yes.
Here, this one.
Yes.
Are you able to say what is the main ingredient in your simulation that can generate this quantity of stellar?
Let me think. So that's a nice question. Why in the simulation is forming like that? Yes, I think that I will have to. let me think, to do a more orbit analysis, I think. I don't know if I have an answer. I mean, why in the simulation is generating with this? Yes.
It would be nice to see.
Yes. Yes. For me, it was really interesting to see that it didn't pass too much time after bar formation. It's happening something that the bars become unstable right after the formation of the bar. But yes, I will have to see about that.
Does it depend on the mass of the galaxy?
No, I don't think so. No, I don't think that it's because they are all very Milky Way like galaxy. They are very similar in between each other. But yes, that's it. Yes, that's a good question to.
It could be nice also. I don't know if you are planning to do any kinematic studies using the simulation. I don't know if
in the second part. In the second part, yes.
You can derive.
Yes. With the stars and
stars and gas.
Yes, because it was this formation and evolution and try to understand in the detail the resonance and how, because you usually have your boxy peanuts made by young stars, but then when you have your boxy peanuts, the young stars that are formed, how they join to the galaxy. So there are a lot of equations how the presence of boxy peanuts affect the metallicity. So there are a lot of interesting questions that we want to approach, but we start doing all the analysis. Was okay. Let's publish first this paper that is like the general properties, this formation mechanism of the boxy peanuts. Try to do this identify the type formation in a more like with this code, and then we are going to study more physics. Yes. But yes, there are a lot of things to do here. It's very nice. Yeah.
Any other questions? I have another one.
Yes, of course.
I'm not an expert on this, so what is the main difference between the Auriga and TNG 50 simulation?
In general terms, they're quite similar, but the main difference are in how they treat the AGN physics.
Do you have AGN? AGN? Do you have any AGN?
No,
they're not included.
No, but the model that they use for the AGN is different. I think that in the radio mode, so they do that very different. But there is a study where I think that it was from a master student where he analyzed how the different baryonic physics of these simulations affect, for example, the bars. And for example, in particular with this kind of objects, he found that in the TNG, the bars are shorter, are more concentrated. In the Auriga, the disks have more mass. It doesn't affect the pattern speed. So you have a small difference.
Resolution also.
Not the resolution, but one question that I also have is I would really like to do a similar analysis that I did, but with higher resolution. Mm-hmm. I think that's a thing to do. Like how will affect a higher resolution to the results. Mm-hmm. So yeah, but in between the two models, affecting that way at least for the bars. Okay. Thank you.
There are no more questions. Let's thank Paula again.
Thank you.
Any question from Zoom? No?
Okay, thank you.
Thank you for joining us.
Thank you.
Thank you.
Muchas gracias.
A ustedes, gracias. Todo, sí, hay como mucho trabajo. Hay mucho hecho, pero mucho por hacer.
Gracias.
Gracias a ustedes por escuchar.
Yo creo que aquí puedo cerrar sin problema.
¿Eh?
Que creo creo que puedo cerrar sin problema,
Bueno.
pero como esto la deja dar más, a ver.
Bien, bien. Bueno, estuvo bien la parte técnica también,
Sí,
¿no? Como que resultó
Está muy bien, claro, para mí la simulación es un mundo desconocido de todo. Porque, por ejemplo, para la cinemática de este tipo de galaxia, la estelar, como que pinta viene el tipo de campo de velocidad o de dispersión. Hay que ser súper complejo porque, ¿no?
Sí.
Toda la parte del
y es más complejo en cosmológica, digamos.
¿Qué hago?
He estado siguiendo en YouTube lo que he podido.
Bueno, bien, pero estuvo bien la transmisión parte técnica.
Sí, se ha salido bastante bien. Excelente. Es verdad que este trozo aquí se ha quedado así de punto. Yo me imaginaba que en una